Introduction to CMAC. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into CMAC, which stands for Cipher-based Message Authentication Code. This is a fundamental cryptographic primitive that plays a crucial role in ensuring message integrity and authenticity in modern security systems. CMAC is particularly important in cloud environments where data travels across networks and needs to be verified for tampering. Unlike simple checksums or hash functions, CMAC provides cryptographic strength authentication by using block cipher algorithms. The beauty of CMAC is that it builds upon existing block cipher infrastructure like AES, which means organizations can leverage hardware acceleration and proven implementations they already have in place. CMAC addresses a critical security need by answering the question, how do we know this message hasn't been modified in transit and truly comes from the claimed sender? This is especially vital in distributed systems, API authentication, network protocols, and any scenario where data integrity is paramount. What is message authentication? Before we understand CMAC specifically, we need to grasp the broader concept of message authentication. In any communication system, whether it's between microservices in a cloud environment, client-server interactions, or inter-system data exchange, we face two fundamental security challenges. First, integrity. Has the message been altered during transmission? Second, authenticity. Did this message truly originate from the claimed sender? These are distinct from confidentiality, which is about keeping message content secret. You might have perfectly encrypted data, but without authentication, an attacker could manipulate that encrypted data in meaningful ways. Message authentication codes or MACs provide a solution to these challenges. A MAC is like a cryptographic seal on a message. The sender computes this seal using a secret key known only to the legitimate parties. The receiver, having the same secret key, can verify the seal. If anyone without the key tries to modify the message or forge a new one, they cannot produce a valid seal. This is fundamentally different from digital signatures which use public key cryptography. MACs are symmetric, meaning the same key is used for both creation and verification, which makes them much faster but requires secure key distribution. CMAC Architecture Overview. Now let's look at how CMAC specifically works at an architectural level. CMAC is built on top of block cipher algorithms, most commonly AES with 128-bit or 256-bit keys. The fundamental idea is elegant. We are going to use a block cipher in a special chaining mode to process the entire message and produce a fixed-size authentication tag. The process begins with the message being divided into blocks. Each block is typically 128 bits for AES. The CMAC algorithm processes these blocks sequentially in a specific pattern. What makes CMAC special compared to simpler constructions is how it handles the last block and uses special subkeys. CMAC generates two subkeys from the main key through a mathematical operation. These subkeys, typically called K1 and K2, are derived by encrypting a zero block and then applying specific polynomial multiplications in a mathematical structure called a Galois field. Do not worry if the math sounds complex. The important point is that these subkeys add cryptographic strength. During message processing, each block is XOR'd with the result from the previous block and then encrypted. This creates a chain where each block's authentication depends on all previous blocks. For the final block, one of our special subkeys is XOR'd in before the final encryption, and the result becomes our authentication tag. CMAC Generation Process. Let's walk through the actual CMAC generation process step by step, because understanding this flow is crucial for implementing or troubleshooting CMAC in real systems. First, we need our inputs, the message to authenticate and the secret key. The secret key must be properly sized for the block cipher we are using, typically 128, 192, or 256 bits for AES. The first operation is subkey derivation. We take our secret key and use it to encrypt a block of all zeros. This gives us an intermediate value. From this intermediate value, we derive K1 by left shifting and conditionally XORing with a special constant. Then we derive K2 from K1 using the same operation. These subkeys will be used to make the final block processing different from intermediate blocks, which is critical for security. Next, we divide our message into complete blocks. If the message length is a perfect multiple of the block size, great. If not, we need to handle that last incomplete block specially. Now we begin the iterative processing. We start with a zero initialization vector. For each complete block except the last, we XOR the current state with the message block, then encrypt the result with our block cipher key. The output becomes the new state, which feeds into processing the next block. This chaining means that any change to any block will cascade through and affect the final result. When we reach the final block, here is where those subkeys come in. If the final block is complete, we XOR it with K1. If it is incomplete, we pad it with a specific pattern and XOR with K2. Then we XOR with our current state and do one final encryption. The result of this final encryption is our CMAC tag, typically truncated to a desired length like 96 or 128 bits. CMAC verification process. Verification is the flip side of generation, but understanding it separately helps clarify the complete authentication workflow. When a message arrives with its CMAC tag, the receiver needs to verify authenticity and integrity. The receiver must have the same secret key that was used for generation. This is a critical security requirement. The key must be distributed securely beforehand through a separate secure channel or key agreement protocol. The verification process starts by running the exact same CMAC generation algorithm on the received message using the shared secret key. This produces a computed tag. The critical step is comparing this computed tag with the received tag. This comparison must be done in constant time to prevent timing attacks, where an attacker tries to learn information about the correct tag by measuring how long the comparison takes. If the tags match exactly, we have two guarantees. First, the message has not been modified, because even a single bit change would produce a completely different tag due to the avalanche effect in the block cipher. Second, the message was created by someone who knows the secret key, because generating a valid tag without the key is computationally infeasible. If the tags do not match, we reject the message entirely. We do not try to guess what might be wrong or accept it anyway. Failed authentication means either the message was tampered with, corrupted in transmission, or is a forgery attempt. In any case, it should be discarded and potentially logged as a security event. Block cipher modes and CMAC. To truly understand CMAC, we need to see how it relates to other block cipher modes of operation. Block ciphers like AES are primitives that operate on fixed-size blocks. To process longer messages, we need a mode of operation. Common modes include ECB, CBC, CTR, and GCM. Each mode has different properties and use cases. CMAC is actually related to CBC mode, which stands for cipher block chaining. In CBC mode for encryption, each plaintext block is XOR'd with the previous ciphertext block before encryption. CMAC follows a similar pattern but with crucial differences. In CMAC, we're not encrypting the message itself, we're creating an authentication chain. The chaining ensures that the final output depends on every single bit of the input message in a cryptographically strong way. What makes CMAC different from just using CBC mode directly is the subkey mechanism for the final block. Early attempts to create MAC functions from block ciphers had vulnerabilities. The subkey addition in CMAC prevents certain classes of attacks, particularly related to message length manipulation. Another key difference is that CMAC doesn't need an initialization vector like CBC encryption does. It starts with a fixed zero state because we're not hiding the message content, we're verifying its integrity. The security of CMAC comes from the secret key, not from randomness in the IV. This makes CMAC deterministic. The same message with the same key always produces the same tag, which is exactly what we want for verification purposes. CMAC versus HMAC comparison. One of the most common questions about CMAC is how it compares to HMAC, which stands for Hash-based Message Authentication Code. Both are MAC algorithms, but they are built on different cryptographic primitives. HMAC is constructed using cryptographic hash functions like SHA-256 or SHA-3, while CMAC uses block ciphers like AES. This fundamental difference leads to several practical implications. From a performance perspective, the advantage can go either way depending on your hardware. If you have AES hardware acceleration, which is common in modern processors, CMAC can be extremely fast. Intel and ARM processors include AES-NI instructions that make AES operations very efficient. On the other hand, if you are using SHA-256 with hardware acceleration, HMAC might be faster. The key takeaway is that both can be highly performant with appropriate hardware support. From a security standpoint, both CMAC and HMAC are considered secure when properly implemented. HMAC has been around longer and has more extensive analysis, but CMAC is based on AES, which is one of the most studied and trusted cryptographic primitives. In terms of standardization, HMAC is specified in RFC 2104 and is widely used in protocols like TLS and IPsec. CMAC is standardized in NIST SP 838B and RFC 4493. One advantage of CMAC is that if your system already uses AES for encryption, you can reuse the same key schedule and hardware acceleration for both encryption and authentication. This can simplify key management and improve overall system efficiency. HMAC requires hash function support, which is a separate requirement. In practice, many systems use HMAC because it has been around longer and has broader library support, but CMAC is gaining adoption, especially in embedded systems and hardware security modules where AES acceleration is prevalent. Security properties of CMAC. Understanding the security properties of CMAC helps us use it correctly and appreciate what it can and cannot do. The primary security property is unforgeability. This means that without knowing the secret key, an attacker cannot create a valid message tag pair, even if they have seen many valid pairs before. The security level is directly related to the block cipher's security. For AES 128, CMAC provides approximately 128 bits of security for key recovery and 64 bits of security against forgery attacks due to the birthday paradox. For AES 256, these numbers increase accordingly. CMAC provides collision resistance in the sense that finding two different messages that produce the same tag is computationally infeasible. This is important for preventing substitution attacks where an attacker tries to replace one valid message with another. The algorithm is also secure against linked extension attacks, which plagued some earlier MAC constructions. You cannot take a valid message tag pair and extend the message while computing a valid new tag. The subkey mechanism in CMAC specifically prevents this. However, it is crucial to understand what CMAC does not provide. CMAC does not provide confidentiality. The message is not encrypted, it is only authenticated. If you need both confidentiality and authentication, you must use an encryption scheme separately or use an authenticated encryption mode like GCM or CCM. CMAC also does not provide non-repudiation. Because it is a symmetric key scheme, both parties can generate valid tags. If Alice and Bob share a key, and Alice receives a message with a valid tag, she knows Bob could have sent it, but she cannot prove this to a third party because she could have generated the tag herself. For non-repudiation, you need digital signatures with public key cryptography. CMAC in network protocols. CMAC has found important applications in various network protocol and security standards. Let us explore where and why it is used. In IPsec, which secures IP communications at the network layer, CMAC can be used as part of the ESP or authentication header protocols to ensure that IP packets have not been tampered with. This is critical for VPNs and secure site-to-site communications. In the realm of wireless networks, CMAC plays a role in securing communications. The IEEE 802.11i standard, which defines security for WiFi networks, includes CMAC as one of the approved MAC algorithms for protecting management frames. This prevents attackers from injecting fake management frames to disrupt network operations or perform man-in-the-middle attacks. CMAC is also specified in the cryptographic message syntax, which is used for digitally signing, digesting, authenticating, or encrypting arbitrary messages. This standard is used in various applications including S/MIME for secure email. In blockchain and distributed ledger systems, while HMAC is more common, CMAC can be used for creating authentication chains and Merkle tree constructions where hardware acceleration is available. The deterministic nature of CMAC makes it suitable for these applications. In industrial control systems and SCADA networks, where embedded devices often have AES hardware accelerators but limited computational resources, CMAC provides efficient authentication for command messages and sensor data. In cloud environments, CMAC can be used to authenticate API requests when both client and server share a secret key. This is an alternative to HMAC-based schemes and can be advantageous when the cloud infrastructure already uses AES extensively. Implementation best practices. Implementing CMAC correctly requires attention to several important details to ensure both security and reliability. First and foremost, use well-tested cryptographic libraries rather than implementing CMAC from scratch. Libraries like OpenSSL, Bouncy Castle, or platform-specific crypto APIs have been extensively reviewed and optimized. When selecting a library, verify that it has been validated against test vectors from NIST or RFC specifications. Key management is critical. The secret key used for CMAC must be generated using a cryptographically secure random number generator. Never derive keys from passwords without using a proper key derivation function like PBKDF2 or Argon2. Keys should be stored securely using hardware security modules or key management services in cloud environments. Protect keys in memory and securely erase them when no longer needed. When implementing verification, always use constant time comparison for the tags. Many cryptographic libraries provide secure comparison functions specifically for this purpose. Never use simple byte-by-byte comparison that exits early on the first mismatch, as this creates timing side channels. Choose an appropriate tag length based on your security requirements. While CMAC produces a full block size output, you can truncate it. Common lengths are 64, 96, or 128 bits. Longer tags provide stronger security against forgery attempts, so don't truncate more than necessary. Be careful with tag truncation in environments where the attacker can observe many authentication attempts. Consider the performance implications of your implementation. If using software implementations, profile the code to identify bottlenecks. If hardware acceleration is available, ensure your library is configured to use it. In high-throughput scenarios, consider batching operations or using parallel processing where possible. Implement proper error handling. Authentication failures should be logged, but error messages should not reveal information about why verification failed. Simply report success or failure. Include rate limiting to prevent brute force attacks on tags. Test your implementation thoroughly using standard test vectors and edge cases like empty messages, messages of various lengths, and particularly messages right at block boundaries. CMAC Key Management. Proper key management is fundamental to CMAC security because the entire security of the system rests on keeping the secret key confidential while making it available to authorized parties. Let's explore key management in depth. Key generation must use cryptographically secure random number generators. Operating systems provide these through interfaces like /dev/u random on Linux or cryptgen random on Windows. Never use standard random number generators intended for simulation or gaming. The key size should match your security requirements. 128 bits for standard security, 256 bits for higher security levels. Key distribution is one of the most challenging aspects. The secret key must be communicated to both parties who will use it, but must never be transmitted in plaintext over an insecure channel. Options include using a separate secure channel established with public key cryptography, physically delivering keys on secure hardware tokens, using key agreement protocols like Diffie-Hellman to derive shared secrets, or leveraging existing secure infrastructure like key distribution centers in Kerberos environments. In cloud environments, key management services like AWS KMS, Azure Key Vault, or Google Cloud KMS provide centralized key storage with access control policies. These services handle encryption of keys at rest, access logging, and key rotation. When using these services, your application code never sees the raw key material. Instead, you make API calls to perform CMAC operations. Key rotation is essential for limiting the impact of potential key compromise. Establish a key rotation schedule based on risk assessment. High security applications might rotate keys daily, while others might rotate monthly or quarterly. When rotating, maintain the previous key temporarily to handle messages that were authenticated with the old key during the transition period. Implement graceful key rollover by accepting both old and new keys for verification during the transition window. Key storage requires protecting keys both at rest and in memory. At rest, keys should be encrypted using a key encryption key, which itself might be protected by a hardware security module. In memory, minimize the time keys remain in plaintext and use secure memory allocation functions that prevent the key from being swapped to disk. When keys are no longer needed, securely erase them from memory using functions that prevent compiler optimization from removing the erasure. Common CMAC vulnerabilities. Understanding potential vulnerabilities helps us implement CMAC securely and avoid common pitfalls. While CMAC itself is cryptographically sound, implementation flaws can undermine its security. Timing attacks are a major concern in MAC verification. If the comparison function exits early when it finds a mismatch, an attacker can measure the time taken to reject different tags, and gradually learn the correct tag byte by byte. This is why we emphasize constant time comparison. The attack can work even over networks if the attacker can make many attempts and average out network jitter. Key reuse across different contexts is dangerous. If the same key is used for CMAC and also for encryption, or if the same key authenticates different types of messages without proper domain separation, it can lead to vulnerabilities. Always use distinct keys for different purposes, or include context information in the messages being authenticated. Weak key generation is a critical vulnerability. If keys are generated from low entropy sources, like timestamps or predictable sequences, attackers can enumerate possible keys. This is why cryptographically secure random number generators are essential. Insufficient key protection leads to compromise. If keys are stored in configuration files with weak permissions, hard-coded in source code, or transmitted over insecure channels, attackers can obtain them. Once an attacker has the key, they can forge any message. Message replay attacks are possible if the protocol does not include additional protections. CMAC only guarantees that a message is authentic. It does not prove the message is fresh. An attacker can capture a valid message tag pair and replay it later. To prevent this, include sequence numbers, timestamps, or nonces in the messages being authenticated. Tag truncation vulnerabilities can arise if tags are truncated too aggressively. A 32-bit tag might seem sufficient, but an attacker has a 1 in 4 billion chance of guessing a valid tag. In high-volume systems where attackers can try many forgeries, this becomes practical. Use at least 64-bit tags, preferably 96 or 128 bits for sensitive applications. Side-channel attacks beyond timing can also affect CMAC implementations. Power analysis attacks can reveal information about key bits by measuring power consumption during cryptographic operations. This is particularly relevant for embedded devices. Cache timing attacks can leak information through the pattern of memory accesses. Protecting against these requires careful implementation and sometimes hardware support, like constant time AES instructions. CMAC performance optimization. Performance is often critical in real-world deployments, especially in high-throughput systems or resource-constrained embedded devices. Let's explore how to optimize CMAC performance. The most significant optimization is using hardware acceleration. Modern CPUs include AES-NI instructions that dramatically speed up AES operations. On Intel processors, this can make AES operations 5 to 10 times faster than software implementations. Ensure your cryptographic library is compiled to use these instructions. On ARM processors, look for similar acceleration features. In cloud environments, select instance types that support these instructions. Software optimization starts with choosing an efficient library. Open Secure Sockets layer is highly optimized and widely used. For specific platforms, native crypto libraries like Windows CNG or Apple Common Crypto might offer better integration. Profile your code to identify bottlenecks. Sometimes the overhead is not in the cryptographic operation itself but in data copying or memory allocation. Batching can improve throughput. If you need to authenticate many short messages, consider whether you can batch them together. The per-message overhead of function calls and setup can be significant for small messages. However, remember that CMAC is inherently sequential. You can't parallelize processing of a single message like you can with hash-based MACs. Memory access patterns matter. Modern CPUs have complex cache hierarchies, and cache misses are expensive. Arrange your data structures to maximize cache locality. Process messages in a streaming fashion when possible rather than requiring the entire message in memory. For very large messages, this also reduces memory requirements. Consider the trade-off between code size and performance. Unrolled loops and pre-computed tables can improve speed but increase memory footprint. For embedded systems with limited memory, smaller implementations might be necessary. Key scheduling overhead can be amortized. The subkey derivation in CMAC can be pre-computed and reused if the same key is used for multiple messages. Many implementations cache this. However, be careful with this optimization in multi-threaded environments to avoid race conditions. For systems with predictable message sizes, specialized implementations can be more efficient than generic ones. If you always authenticate 1,500 byte Ethernet frames, an implementation optimized for that size will outperform a generic variable length implementation. In multi-core systems, while you can't parallelize a single CMAC computation, you can process multiple independent messages in parallel. Design your system to take advantage of this. Use thread pools or async I/O patterns to keep all cores busy. CMAC in cloud security. Cloud computing introduces specific considerations and opportunities for using CMAC in cloud environments. Data frequently moves between services, crosses trust boundaries, and needs authentication at various layers. CMAC provides efficient authentication that is well suited to these challenges. In API authentication scenarios, CMAC can authenticate REST API requests. The API client and server share a secret key. When making a request, the client creates a canonical representation of the request, including the HTTP method, URL, headers, and body, then computes a CMAC over this representation. The CMAC tag is included in a header. The server reconstructs the same canonical representation and verifies the tag. This prevents tampering with the request in transit. AWS uses a similar approach with HMAC in its signature version 4, and CMAC could serve the same purpose with hardware acceleration benefits. Inter-service authentication in microservices architectures is another use case. When services communicate within a VPC, TLS might provide transport security, but additional authentication at the application layer adds defense in depth. Services can use CMAC to authenticate message payloads with shared keys managed through a secrets management service. This is particularly useful for asynchronous messaging through queues where the sender and receiver might not have a direct connection. Data integrity verification for cloud storage is important. When storing data in object storage like S3, You want to verify that data has not been corrupted or tampered with when you retrieve it. Computing a CMAC over the data before storage and verifying it after retrieval provides this assurance. Cloud providers often offer integrity checks, but client-side verification with your own keys provides stronger guarantees. In serverless architectures, where functions are short-lived and stateless, CMAC can authenticate event data. When an event triggers a Lambda function or cloud function, authenticating the event payload ensures it has not been tampered with. The event source and function share keys through the cloud provider's secrets management. Key management in the cloud leverages services like AWS KMS, Azure Key Vault, or GCP KMS. These services store encryption keys in hardware security modules and provide APIs for cryptographic operations. You can use them to manage CMAC keys with fine-grained access controls, audit logging, and automatic rotation. Your application code calls the service to perform CMAC operations without ever handling raw key material. Container orchestration platforms like Kubernetes can use CMAC for authenticating configuration data or securing etcd communications. Kubernetes secrets can store CMAC keys, and admission controllers can verify CMAC tags on resource definitions before applying them. CMAC standards and specifications. CMAC is defined in several formal standards and specifications that ensure interoperability and provide detailed implementation guidance. Understanding these standards helps when implementing CMAC or evaluating implementations. The primary specification for CMAC is NIST Special Publication 838b titled, Recommendation for Block Cipher Modes of Operation, the CMAC mode for authentication. This document, published by the National Institute of Standards and Technology, provides the authoritative definition of CMAC including the algorithm description, security considerations, and conformance requirements. NIST SP 838b specifies CMAC as applicable to any approved block cipher, though it focuses on AES. The document includes detailed mathematical descriptions, security analysis, and guidance on parameter selection. It's freely available from the NIST website and is essential read for anyone implementing CMAC RFC 4493, titled, The AES CMAC Algorithm, provides an IETF specification of CMAC specifically for use with AES. This RFC includes the algorithm specification, test vectors, and security considerations. It was published in 2006 and focuses on making CMAC accessible to the Internet Protocols community. The test vectors in this RFC are particularly valuable for validating implementations. ISO/IEC 97971 is an international standard that specifies MAC algorithms including CMAC variants. This standard is part of a family of standards on message authentication codes and provides a broader context for CMAC within the landscape of MAC algorithms. While ISO standards require purchase, they provide formal specifications recognized internationally. The CMAC algorithm is also referenced in NIST's Cryptographic Algorithm Validation Program. Implementations can be submitted to NIST for validation testing to ensure they correctly implement the standard. Validated implementations receive a certificate number that can be referenced for compliance purposes. This is important for systems that need to meet FIPS 142 or FIPS 143 requirements. In the context of IPsec, RFC 4494 titled, The AES CMAC 96 Algorithm and its use with IPsec, specifies how to use CMAC with IPsec protocols. It defines CMAC 96, which is CMAC with the output truncated to 96 bits, as this provides a good balance between security and overhead for IPsec authentication headers. For IEEE 802.11 wireless networks, the IEEE 802.11i standard incorporates CMAC for protecting management frames. This prevents various attacks on Wi-Fi networks and is part of WPA2 and WPA3 security. Understanding how CMAC fits into these standards helps when securing wireless networks in enterprise or cloud environments. Testing and validation. Thorough testing and validation are critical for CMAC implementations to ensure both correctness and security. Let's explore comprehensive testing strategies. Start with test vectors from authoritative sources. NIST SP 838b and RFC 4493 provide official test vectors that cover various scenarios including different message lengths, keys, and edge cases. Your implementation should produce exactly the outputs specified in these test vectors. Run all provided vectors and ensure 100% pass rate. Any deviation indicates an implementation error that must be corrected before deployment. Unit testing should cover edge cases systematically. Test with empty messages, single block messages, messages that are exactly multiple blocks long, and messages with partial final blocks. Test with different key sizes if your implementation supports multiple key lengths. Test subkey generation independently to ensure K1 and K2 are computed correctly. These subkeys are critical to security, and errors here can completely compromise CMAC. Integration testing verifies that CMAC works correctly in your larger system. Test the complete flow of message generation, transmission, and verification. Include tests for correct message acceptance and incorrect message rejection. Test with corrupted messages to ensure they are properly rejected. Modify single bits at various positions in both the message and tag to verify that corruption is detected. Performance testing establishes baseline performance and identifies regression. Measure throughput for messages of various sizes. Create performance profiles for your typical workload. Test under load to ensure performance remains acceptable. Monitor for memory leaks or resource exhaustion under sustained operation. Security testing goes beyond functional correctness. Test for timing side channels by measuring verification time for correct and incorrect tags. The time should be identical. Test that key material is properly cleared from memory after use. Use memory analysis tools to verify no key material remains in freed memory. Test error handling and ensure error messages do not leak sensitive information. Compliance testing verifies adherence to standards. If your system needs FIPS validation, submit your implementation to NIST's validation program. Even if formal validation is not required, using the CABP validation test vectors provides confidence. Test against requirements from relevant standards like RFC 4493 or ISO specifications. Regression testing ensures changes do not break existing functionality. Maintain a comprehensive test suite that runs automatically on every code change. Include all test vectors, edge cases, and integration tests. Use continuous integration systems to run tests automatically. Interoperability testing verifies compatibility with other implementations. Generate messages and tags with your implementation and verify them with reference implementations like OpenSSL. Generate messages with reference implementations and verify with yours. This catches subtle incompatibilities in encoding or parameter handling. CMAC alternatives and when to use each. While CMAC is excellent for many use cases, it is important to understand alternatives and when each is most appropriate. HMAC is the most common alternative to CMAC. HMAC uses hash functions like SHA-256 instead of block ciphers. Choose HMAC when you need maximum interoperability as it is more widely supported in libraries and protocols. HMAC is excellent when you are already using hash functions in your system or when hardware acceleration for AES is not available. HMAC SHA-256 is the de facto standard for many applications including TLS, SSH, and OAuth. Choose CMAC when you already have AES infrastructure for encryption and want to reuse it for authentication. CMAC is ideal when AES hardware acceleration is available, such as in modern CPUs with AES-NI or embedded systems with AES crypto accelerators. CMAC can be more efficient in these scenarios. Poly 1305 is a modern MAC designed by Daniel Bernstein. It is extremely fast in software implementations and is used in combination with CHA-CHA-20 for authenticated encryption. Choose Poly 1305 CHA-CHA-20 for systems where AES hardware acceleration is not available but high performance is needed. This combination is popular in mobile devices and is used in TLS. GMAC as the authentication component of the GCM authenticated encryption mode. If you need both encryption and authentication, GCM is often the best choice as it provides both in a single efficient operation. GMAC alone can be used for authentication without encryption. Choose GMAC when working with protocols that already use GCM for some communications. SIP hash is designed for hash table keys and provides protection against hash flooding attacks. It is not intended for general message authentication but is perfect for its specific use case. Blake2 in MAC mode is a modern hash function that can be used for authentication. It is faster than SHA-2 in software and has a simpler design. Choose Blake2 when you want modern cryptography and are building new systems without legacy compatibility requirements. Carter-Wigman MACs like UMAC provide extremely high performance, especially for long messages. They are more complex to implement correctly but can be worthwhile for specific high-throughput applications. Digital signatures using RSA or ECDSA provide authentication with non-repudiation. Choose signatures when you need to prove to third parties who created a message or when the parties do not share a secret key. Signatures are much slower than MACs but provide stronger authentication properties. The decision often comes down to your specific requirements. What cryptographic primitives do you already use? What hardware acceleration is available? What are your performance requirements? What level of standardization and interoperability do you need? For new cloud-native applications with modern infrastructure, CMAC with AES-256 is an excellent choice that provides strong security with good performance. Real-world CMAC applications. Let's look at concrete real-world applications where CMAC provides critical security. In financial systems, CMAC authenticates payment messages between banks and clearinghouses. When a bank sends an electronic funds transfer message, it computes a CMAC over the transaction details including account numbers, amounts, and timestamps. The receiving bank verifies the CMAC before processing the transfer. This prevents unauthorized modification of payment amounts or redirection to wrong accounts. The financial industry uses hardware security modules that provide AES acceleration, making CMAC very efficient for high-volume transaction processing. In automotive systems, particularly in modern connected and autonomous vehicles, CMAC authenticates messages on the CAN bus. The controller area network is the primary communication network inside vehicles, connecting the engine control unit, brake systems, steering, and other critical components. Without authentication, an attacker with access to the CAN bus could inject malicious commands. CMAC provides lightweight authentication suitable for the real-time requirements of automotive systems. The limited message sizes in CAN bus communication match well with CMAC's block-oriented processing. Industrial control systems use CMAC to authenticate SCADA commands and sensor readings. When a control center sends a command to open a valve or adjust a set point, CMAC authenticates that the command is legitimate. When sensors report temperature, pressure, or flow rates, CMAC ensures the data hasn't been tampered with. These systems often run on embedded devices with AES hardware accelerators, making CMAC more efficient than software-only alternatives. The criticality of these systems means authentication failures must be handled reliably, and CMAC's deterministic nature helps with this. Satellite communications employ CMAC for authenticating telemetry and command messages. The high latency and occasional communication errors in satellite links make reliable authentication important. CMAC's resistance to bit errors through its all-or-nothing property ensures that corrupted messages are properly rejected. The bandwidth constraints in satellite communications favor CMAC's fixed overhead. Military and defense applications use CMAC in secure communications equipment. Tactical radios, secure phones, and encrypted data links use CMAC for message authentication. These systems often have stringent certification requirements that CMAC's FIPS validation can help meet. Blockchain and distributed ledger systems can use CMAC for creating authentication chains and verifying message integrity between nodes. While many blockchain systems use hash functions, permissioned blockchains might use CMAC for authenticating inter-node communications. Smart grid applications authenticate commands to power distribution equipment and verify meter readings. The large-scale deployment of smart meters and grid automation equipment makes efficient authentication essential, and CMAC provides this while meeting the security requirements of critical infrastructure protection. Future of CMAC and post-quantum considerations. As we look to the future of cryptography, particularly in the context of quantum computing threats, it is important to consider CMAC's longevity and potential evolution. CMAC's security is based on the block cipher it uses. Typically, AES current understanding suggests that quantum computers using Grover's algorithm could reduce the effective key size of AES by half. This means that AES 128 would have 64-bit effective security against quantum attacks, while AES 256 would have 128-bit security. This is a significantly different threat profile than for public key cryptography, where Shor's algorithm completely breaks RSA and ECC for CMAC. The practical implication is that AES 256 provides reasonable post-quantum security for symmetric authentication. Organizations planning for the quantum future should migrate to 256-bit keys if they haven't already. The good news is that this migration is straightforward compared to replacing public key systems. CMAC's structure itself doesn't need to change, it simply needs to use quantum-resistant block ciphers. The NIST post-quantum cryptography project is primarily focused on public key algorithms, but it is worth monitoring developments in symmetric cryptography as well. Research into quantum-resistant block ciphers continues, though AES is considered reasonably secure with adequate key sizes. As quantum computing advances, CMAC implementations might need to support larger key sizes or alternative block ciphers. The flexibility of CMAC's design, which can work with any block cipher, is an advantage here. If new quantum-resistant block ciphers emerge, CMAC can adopt them without fundamental algorithm changes. Hardware acceleration will continue to evolve as new processor architectures emerge, including potentially quantum-resistant cryptographic accelerators. CMAC implementations can leverage these. Cloud providers are already investing in custom silicon for cryptographic operations, and this trend will likely continue. Standardization efforts will need to address post-quantum security explicitly. Future versions of NIST SP838B might include guidance on key sizes for quantum resistance, recommendations for quantum-safe block ciphers, or transitions to alternative MAC algorithms if necessary. In the near term, CMAC remains a solid choice for message authentication. Its basis on well-studied block ciphers, hardware acceleration support, and clear migration path for quantum resistance make it suitable for long-term deployments. Organizations should focus on proper key management, using adequate key sizes, and staying informed about cryptographic developments rather than worrying about immediate quantum threats to CMAC. Conclusion and summary. We have covered CMAC comprehensively, from its fundamental principles to advanced implementation considerations. Let's summarize the key takeaways. CMAC provides cryptographically strong message authentication using block ciphers like AES. It guarantees that messages have not been tampered with and authenticates the sender's identity through shared secret keys. CMAC is particularly efficient when AES hardware acceleration is available, making it ideal for modern processors and cloud infrastructure. The algorithm uses a clever subkey mechanism to provide security against various attack types including length extension attacks. Understanding the generation and verification process helps implement CMAC correctly and troubleshoot issues. Proper key management is absolutely critical. All the cryptographic strength of CMAC means nothing if keys are poorly generated, insecurely stored, or improperly distributed. Security best practices include using constant time comparison for tag verification, implementing appropriate error handling, and protecting against side-channel attacks. Performance optimization leverages hardware acceleration, careful memory management, and efficient library selection. CMAC compares favorably to alternatives like HMAC, with the choice depending on specific system requirements, existing infrastructure, and performance needs. Real-world applications span from financial systems to automotive networks, demonstrating CMAC's versatility and reliability. Looking forward, CMAC has a clear path to quantum resistance through adequate key sizes and potential migration to quantum-safe block ciphers if needed. For cloud and network security engineers, CMAC is a valuable tool that provides efficient authentication with strong security guarantees. Whether securing API communications, authenticating microservices messages, or protecting IoT device communications, CMAC offers a standardized, well-analyzed solution backed by extensive cryptographic research and practical deployment experience. Thank you for your attendance. Please consider subscribing to the channel.